Swayam Prabha. Digital India. Educated India.
Welcome to 10th lecture of video course on Tribology. The title of this lecture is Wear Analysis. In previous 4 lectures, we have discussed various mechanisms related to wear. Now, today's lecture is related to how to analyze some failure related to wear. Can we go ahead systematically, point by point? Can we pinpoint what kind of wear mechanism is taking place and how we can get remedy of that? How can we reduce that kind of wear mechanism? In true sense, there will never be a single wear mechanism which will cause a failure. It will be generally related. One wear mechanism will promote another wear mechanism. So, generally they are integrated one way or another way. Thinking only one wear mechanism may not give 100% solution. In addition to that, we need to know that there are too many system parameters which affect the wear mechanism. So, we need to think out of box whenever we attack this kind of problem. We need to find alternative solution from the load point of view, from system point of view, from materials point of view, from lubrication point of view. Quite possible one solution may be better solution compared to other solution. Otherwise, every solution will provide some results, comparative results, but we should choose the best solution. So, first question comes in our mind, can one estimate the wear rate? I believe yes. We have derived the equation for adhesive wear, we have derived the equation for abrasive wear, we have derived the equation for erosive wear and fatigue wear also. Using those equations, one can estimate wear rate. So, question answer is yes, we can estimate the wear rate. But Professor Ludema, Michigan University, he disagrees with that. He says that, or I am quoting his sentence, the overall it is probably accurate to say that there is a little incentive for a designer to use any of your equations available in the literature. What is the reason for that? He provides the reasons also. He says a scan of many wear models shows considerable ingredity or inconsistency. There is some variation from one equation to other equation, and people are not coming or converging to one equation except the Archer's model. What are the reason is the equations have either too many undefined variables or too few variables or too many lesser number of variables to adequately describe the system. Both the complexities, either the system is not being identified properly or there are too many variables which cannot be determined by few experiments. You have to do a number of experiments to come to the results. So, using directly equations or using wear equation directly may not give complete solutions. We need to think from other angle. In addition, above all this what the sentence comes is most of the available equations are derived made for mild wear rate of the components. What is the meaning of that? At wear rate, if it is under mild domain, a mild regime, then only can be predicted. In severe wear case, it cannot be predicted. Or we can say, if we are rejecting some component, it is because of severe wear, because of the high wear rate, that is why we are rejecting. Mild wear we will not be rejecting so fast, or rejecting severe wear will not be easy for us. If it is a severe wear, then we are rejecting, but we will not be able to diagnose what is the wear mechanism. Severe wear may come with a number of combination of wear mechanisms. So, finding a root cause failure will be always a difficult situation by using a one single equation. Instead of that, we should always go ahead with root level, or we start always with the scratch level, try to diagnose what are the forces, how the forces are getting transferred from one surface to other surface, are they really intentionally they have been transferred, or because of the some system problem they are getting transferred. So, a number of situations are possible. So, it will be always advisable to go ahead one step by step sequentially and try to analyze. If we directly jump, see the wear and find out, okay, we try to find out, okay, what will be wear mechanism, that may not be good results. Finally, from this slides comes, so the conclusion from this slide says that to estimate wear, theoretical equations as well as experimental coefficients are required. That means, we cannot get 100% results just by physical relations. We need to have experimental coefficients or experiments performed on the system to get the results. We can do comparison. If we want to compare 2 materials, 4 materials, or compare to 2 system designs, then wear equations or theoretical equation may give good results, but we want to find out absolute sense the life, then we need to find need to use experimental coefficient too. Let us take one example. This slide shows a cam which has some sort of pits on the surface. This cam was rejected because it was making some noise and it was not performing its intended function. And this portion shows clearly what are the number of pits, and if I take some reference axis 0 degree here and rotate by 190 rotated by 270 degree. So, this kind of wear occurs roughly 270 degree, 270 plus or minus some degree. If I take reference axis over here, then this will turn out to be around 90 degree. That is why this heading comes, this wear has occurred at the 91 degrees. That means, there was a reference axis over here and 91 degrees over here. If I am assuming the rotational motion is clockwise. Can we do systematic approach, or can we follow systematic approach to estimate this kind of pitting life of cam follower? Even though in my previous slide I mentioned that wear will not occur alone, it will be a combination of wear mechanism which will work together. However, this was precision related operation. So, wanted to be this portion was this cam was rejected much earlier stage, just within 1 year it was replaced with a new cam. They wanted accuracy, and interesting point is that this cam was used for filling the toothpaste in tube. So, reduction in quantity or more quantity was a bad quality, and they wanted to maintain the quality of toothpaste in tube proper quantity. That is why they rejected at the earlier stage, so that there should not be much problem. And we can say we can start with the pitting wear, even though I mentioned that always a combination will work, but here the pitting wear is happening. So, I am going to analyze it along as a pitting wear, but it can be combined with some sort of corrosion, because pitting is always aggregated if there is a moisture, if there is a corrosive environment. So, I showed only the cam, but it is also related to the follower. The cam follower, they are generally used as a one unit. In addition to that, question comes, can we operate this mechanism at the higher speed? Because if I go ahead with the straight back curve, I know that if I speed of operation is increased, then wear coefficient will decrease and friction coefficient will decrease, or friction coefficient will decrease, that is why the wear will decrease. So, question comes, can we really operate at slightly higher speed compared to what we are operating? If I assume this cam was operated at 60 rpm, can I think about operating 65 rpm? What will be benefit of that is more faster filling of the toothpaste will happen because of higher rpm, and if we are able to gain 4%, 5% production that will help us, or that will overall give the good returns. So, first is that how to analyze the speeding failure. Second, can we think about increasing the speed without much problem, or if a speed is going to reduce the wear, increase the life, we should opt for that. So, first question, how does speeding failure occurs, or how does speeding failure occur? I am showing two blocks, one is yellow color block, other one is a blue color block, and here the double headed arrow is shown, that shows that stresses or load will be reversible in nature. It will be applied and relieved, applied and relieved. Now, blue color block says some sort of the stress profile, and this stress is shown only a shear stress. We are not showing a compressive stress. There is a reason for that. We know pitting occurs generally because of shear stresses. It is not because of compressive stresses, or in other words, we can say one direction is a compressive stress, but that is inducing the shear stress in lateral direction, that causes a fracture, that causes a failure. An interesting thing is that shear will be lesser at the surface and shear stress will be higher at the subsurface. That is why many times if there is no surface crack available, fatigue will start from the subsurface, and if there is a one crack, subsequently other crack, and they merge together, they become bigger in size, unstable, and the fracture will occur. So, just keeping this thing in mind, we are starting. Now, it has been mentioned that this kind of pitting failure is happening because of the reversible loading, because of the dynamic loading, because of change in the magnitude of the load. Now, can we really reduce this magnitude? First thing, and from second thing is that from where this load is coming. If I apply a constant load, then can we really remove or avoid this kind of failure? Can we say that this kind of failure will not occur? So, first we did estimation of the force which is getting transferred from cam to follower, and cam is also experiencing a reaction force. So, this force is changing with a degree with a rotational angle. As the cam rotates, it experiences a different kind of forces. You can see here the force is roughly 1200 Newton, steady for some time, then it goes down, then goes up. Maybe the maximum value in this cycle is a 90 degree. At the 90 degree, the load is high. Again, it remains to a stationary position from roughly 122 degree to 240 degree or 243 degree. It remains stationary, it does not change, it is static. After that, again the shoots up, it goes on higher value, crosses compared to this magnitude, and the maximum value occurs around 270 degree, and then again goes back to the lower value, dips, and again rises. And here what we are referring from the top axis. If I go back, this is what I am saying, that this is the axis, I am assuming 0 degree a rotation, and this is 270 degree exactly. So, whatever we are thinking that pitting wear has occurred at the 270 degree, the same thing is been shown over here. The maximum force is around 270 degree, but I cannot conclude just by finding the force, how much force is generated at the interface. We need to do more analysis. One positive point is that we found the failure at around 270 degree, and we found the failure because of the high load. That is the one possibility, that high load is there. Now, question comes that can we really reduce this load, or can we reduce the dynamic variation in the load, can we bring to the steady state condition. So, this is what slide says, can dynamic load be reduced? Interesting thing, yes, it can be. Now, if I find the pressure angle variation with the cam angle, with the rotation of the cam, how pressure angle is varying. It says that pressure angle is 0, it reaches to 42 degree in negative direction, then it remains stationary from around 120 degree to 240 degree, then it goes up, and maximum pressure angle is 45 degree. If I reduce this pressure angle, dynamic load will reduce. You can see the comparison. Wherever the pressure angle is maximum, load is maximum. Here again the load is maximum over here, sorry, pressure angle is maximum here, the load is also maximum over here. And this load is a vector combination as a vector sum of the two components. That is why the negative sign is getting mixed. It is not a, we are not showing any negative sign, it is a vector sum and that will remain positive. It is a magnitude, it is not a with direction. So, if we can reduce or we can redesign the system with a lesser pressure angle, this load will decrease and overall life of the cam will increase. To give a complete definition to the pressure angle, we can say the pressure angle is the angle between direction of motion and axis of transmission or axis of the load transmission along which the load is getting passed. Okay. And this gives a couple of good indications to us. First thing is that if the pressure angle is 0, it is not changing, what we can say, transmitted force is completely utilized to move the follower. So, it is fulfilling the complete intended purpose. We are applying force to move the object, to move the follower, and it is moving in the same direction. It is not changing its direction and 100% force is getting transmitted. What it is fulfilling its intended function. However, if the phi is equal to 90 degree, you are applying a force, object is not moving at all. That means 100% force is misused, or we say that it is not utilized at all. It is inducing the stresses, but it is not giving any other useful function to us. So, we should avoid phi 90 degree, we should always encourage phi 0. But we know the path motion and because of the variation in a motion, there will be always some pressure angle. If we go for the better design, larger radius, this pressure angle can be reduced, but it will occupy more space, and space constraint will always be there. It is going to increase the size of the machine. So, we will always look for the lower size machine. So, there will be always a trade off. We can't say that pressure angle 0 is possible, it is possible, but because of some other constraints we will not be going pressure angle 0 always. Maybe the few degrees, some chunk, yes, that is also shown here from 120 degree to 240 degree. Pressure angle is almost 0 and the force is steady. Another word, this much force is sufficient to give our purpose. This steady component is sufficient to fulfill the function, but additional force is coming because of the pressure angle, because of the force in other direction is getting diverted, and then why we need to increase the pressure. More load is required, almost a 2 time load is required compared to this. So, we can go for the better design. You can reduce the pressure angle, we can reduce the dynamic load. Can we bring we can bring to the steady value. The first constraint comes that we cannot bring phi is equal to 0 always because of the path motion. There will be some finite value greater than 0 for some angle, maybe say the 60 degree, 70 degree, that will increase the load. But in addition to that, if I pressurize too much, now I want always the pressure angle is 0 and we want force to be transmitted. So, that load, dynamic load is not there and there should not be any failure of cam. It should sustain infinite life. That can also be done, we can argue on that, we can go for a better design, we can go for complete dynamic design, multi-body dynamics can be used. But question comes, will that be a 100% solution to us? So, this slide poses a question, can dynamic load be eliminated? To answer this question, it is always preferable to see how cam follower mechanism is really functioning. What is interaction between cam and follower? So, this is a grooved shape cam and follower which is not visible to us is somewhere here, is moving in groove. And there is a link, there is a follower is here, sorry, follower is moving in this direction, this is another link for support. The follower moves in this path and some clearance is provided for free motion. So, that is why I say that this is a radial cam and it is trapping roller follower, which roller follower is here. We provide some clearance so that cam can rotate about its own axis. It is rotating about the cam axis also, instantaneous cam axis, but we want it should freely move about its own axis. However, there will be a lot of friction, there will be sliding, and we want a pure rolling motion. We know pure rolling will have a lesser coefficient of friction, a much lesser coefficient of friction compared to sliding friction. So, it is always advisable to keep some clearance that can be decided, and how much clearance is just sufficient, which is not creating any problem of the contact and not creating problem of the sliding. But when we see this kind of mechanism, we understand there is a clearance and we are allowing roller to rotate about its own axis, and it is also rotating about the cam axis, instantaneous cam axis. Then this point comes, the loading and unloading is inherent in rolling contact, or even though we can try pressure angle, we can bring pressure angle to 0, but because of this loading and unloading which happens at the rolling contact, that is going to introduce some sort of dynamic load. So, pressure angle making 0 is not going to fulfill the function, it is not going to give us the desirable results. Even though we do all the things, we make a good mechanism, we go for the multi links, try to make pressure angle as low as possible to 0, as close to the 0 as possible. But still in that case, because of the rolling contact nature, there will be loading and unloading. That means, there will be a force and there will not be force, and it will be generating a dynamic load. To understand that, let us take a look, or just go through this slide. We said there is a blue color, I am assuming this is the follower, and there is a line, a straight line, assuming the cam radius is much larger, much larger compared to the follower radius. So, can be approximated as a flat surface, or we can make effective radius and give complete effective radius to the roller and make this cam surface as a infinity radius. Now, in any condition when this follower is stationary on the cam surface, nothing happens. If it is not subjected to the load, nothing happens, it just remains there. Now, if we apply load, there will be some parabolic distribution of the force or parabolic distribution of the pressure generated at point contact or line contact. I am assuming the line, assuming that the follower has some finite length. So, it is the line contact. Applying a force, line contact will be turning out to be elliptical contact or rectangular contact, and pressure will be maximum at the center, minimum at the edges of that contact. It will not be stationary. Now, if of course, this stress which is generated, or the pressure which is generated in a surface is known as the contact stresses or Hertzian stresses. Hertzian was the first person who could estimate this kind of stresses. That was his formulation, which we generally use under dry condition when there is no lubrication, and assuming the coefficient of friction is 0, we can utilize his expression directly. He gave expression for the slender versus slender contact, and we can find out what will be the contact patch and how pressure will vary, but that is the ideal situation. And using this formula, we can think about the contact stress as a function of radius of follower and radius of cam. This clearly indicates that cam radius need to be larger than follower if there is a negative sign. If there is a positive sign, then any combination is fine, but generally we use a positive sign if both the surfaces are convex. We use a negative sign when the one surface is concave, another surface is convex. In our mechanism, both the surfaces are working. We have a convex contact and we have concave contact. How that is going to be described in a following slide. But what is the interesting point which we can gain from this is that as the radius is increasing, contact stresses will go down, will reduce. Similarly, if the cam radius is increasing and if it is a convex, then we can say again contact stresses will be reduced. However, if there is a concave and convex combination, then overall combination will be having lesser results. We can say that convex and concave interface will induce lesser contact stresses compared to convex and convex shape. That is why we need to always think over, do we really we recommend a convex convex or convex concave interface. And as I mentioned that in our case study or cam follower study, both the combinations are there. Now, to find out whether really a dynamic load is inherent, this slide, this picture exemplify that. It says that now load is applied and we know that follower is going to rotate about its axis. It is slightly away because of the pressure profile, even if it is not coming very near to that, this surface will be experiencing some stresses. That is why I shown the low magnitude stress. I am just showing with a line the some magnitude. We are not saying that it is absolute, it is just a comparative purpose. Some magnitude is there. Now, if it rotates slightly towards the line, then this magnitude is going to increase. That means, initially it was point was like here, now it has come somewhere here. The pressure, contact pressure will increase, that will increase the contact stresses. And if it is a continuum, the direct load or we say that point of contact or line of contact directly comes on top of this point, then stress will be maximum. As it is continuously rotating, it will move away from the point, stress will reduce. Again it will move away from the point, further stresses will reduce and finally it will come to 0. So, just because of the rolling action, same point is subjected to the x unit of stress, phi x unit of x stress and tan x unit of stress. And again, as a roller passes that point, is coming back to from tan x to phi x and from phi x to 1 x and 1 x to 0 x. So, whatever we do, rolling contact are going to give us dynamic load. It is going there, and this kind of interface is always going to give us variation in stress, maybe from 0 to maximum compressive stress, and that is going to introduce some sort of shear force in a surface or some surface. Now, what in the last slide we mentioned about convex and concave interaction, and I have a dock in cam follower magnifier and dock in this. You can say this portion in contact with the roller follower is going to give us a convex shape. This is a convex shape and this is a convex shape. So, interaction is a convex. As there is some clearance, it moves from this point to this point. This convex shape will come in contact with the concave shape, that is shown over here. This is a convex, this is a concave. So, one cam roller follower is generating convex as well as convex concave in one complete rotation. We can shape or we can find out the radius of cam. You say initially this is the convex shape, and after that as this radius is going to act. So, this will be concave shape radius. We can model cam follower like that. An interesting thing is that this has a number of points. We know cam is continuous phenomena, but to analyze it we need to divide a number of points. So, that we can find out the load, we can find out the radius as those points, those divisions and get the results. In for convenience we have divided in 25 division. So, we are able to find out what are the 25 loads on discrete point and what are the geometry parameter, the radius of cam on this. And if I do a proper numbering, what we can say, convex shape occurs or convex contact occurs from point 8 to 18. So, this is a point 8, 9, 10, 11, 12 up to 18. If I keep a follower on top of that, from 8 to 18, this is a convex shape, interface. From point 1 to 7, the starting point suppose is here, 1 to 7, that is a concave shape. Similarly, 19 to 25, this is a convex shape, convex concave interface. And interesting thing is that from 7 to 8, it goes through transition. Similarly, 8 to 19 goes through the transition, and this transition is going to introduce sliding. It is going to lose rolling motion, and most of the sliding will be getting introduced because of this transformation from convex convex to convex concave. And we say this transfer which is introducing sliding, and that sliding is reducing the cam life. So, we should work on this. Can we reduce the sliding? If it is possible, that will give us good results. So, question comes, we have quoted that sliding is going to reduce the life, then how sliding reduces the life? Again the same figure is shown, which shown in previous couple of slide previous to this. Says that there is a yellow block subjected to reversible load. Explanation was given why the load is dynamic, and then blue block is experiencing some shear stress, which is a determinantal, or it is creating some problem. It is going to generate some sort of cracks. It is going to generate some sort of voids in a surface, but not immediately, maybe after number of cycles, right. Now, if there is a sliding introduced, then what will happen? We need to have some sort of friction force to push it, because this force will be much larger than a rolling friction force. So, we are introducing additional force over here in the tangential direction, and that tangential force is going to increase the tau max value. That is says that it is not only increasing the magnitude, but it is shifting also. You can see here the maximum value is over here. The maximum value has increased and is going closer to the surface. If it is going closer to the surface, then removing a piece of this blue block will be easier. So, it is doing both the things. First, it is giving high stress, and it gives a very close high stress to the surface or near to the surface, which will reduce the life in twofold, in two ways. If I assume total pitting life is NF, number of cycles are NF, when there was no crack, non-cracking life, that is N0, crack initiated, and after that there is a propagation. Crack is moving from subsurface to surface, NP. Now, if the shear stress magnitude is increased, we know very well this N0 will come down, the reduction in N0. Further, if this maximum value is shifted towards the crack, towards the surface, that means crack is generated very near to surface, immediate pit will be there. That means it is also going to reduce NP, or we say that when sliding is coming into picture, it is reducing N0, it is reducing NP. So, overall life is getting reduced. To demonstrate that, let us take again maybe some section of this blue block. We say there is no crack. After N0 cycle, there is some crack generated over here. We can find out. And after NF cycles, we are saying that this NF cycles are after N0. That means, once it reaches to N0, counter again starts. 1 to NF, it is not NF is not sorry, in this case counter starts and 1 to NP comes, and this will be a summation. Yeah, it will be NP plus N0. This counter is not starting here, it is starting from 0 from the first cycle itself. If it is NP, then we can say that after N0 we are going to again restart the counter from 1, and that is from 1 to NP, this kind of failure will occur. Or if summation comes n0 plus np, we can say after nf cycles first bit is going to generate it. When the first bit is generated, then there is a compromise on the surface. So, rough surface comes, there will be some sort of jumping mechanism or jumping phenomena will occur, that is going to create more disturbance in smooth flow, and that is going to generate further more number of more number of cracks because of the impacting. Now, if I go ahead with Hudson theory, contact stress theory, what we can get instead of 25, I have used a few divisions, so that it can be accommodated in one slide, and we have figured out cam contact radius everywhere. Follower contact radius is always constant, follower radius is not changing. We are assuming that wear happens on the follower surface is negligible compared to the follower radius, and the normal load which is coming on the surface has been estimated based on the force geometry. We can find out what will be the maximum compressive stress, maximum compressive stresses which are estimated using the Hudson theory. We find that stresses are increasing, first decreasing then increasing, it reaches to maximum value over here 453 megapascal, and again it reduces, it reaches to around 270, roughly 473 megapascal. So, we know very well the load was higher, similarly the stresses are higher, it is coming roughly 473 megapascal. Again after that it reduces and reaches to the minimum value which we have estimated at 0 degree, the same 0 and 360 degree we know they will merge. This is one of the validation point, we can say the 0 and the 360 should give the same results, whatever way may we get the results, it should complete one cycle. Now, as I mentioned earlier, the compressive stress will not initiate fatigue process, but shear stresses which are associated with the compressive stresses causes the crack formation, and once the crack is formed after the repetitive loading, we will load unload it and close the crack, open the crack, close the crack, open the crack, and it will enlarge slowly and finally the fracture will occur, or finally a pit formation will occur. And if the sliding is introduced, pit formation will be much earlier. So, what I am trying to conclude from this slide, the Hudson theory is not sufficient to give explanation for the pitting wear. First thing, we need to find out what are the associated shear stresses which are generated at the subsurface or at the within the surface. In addition to that, if the sliding is introduced, how the shear stress is going to move up, how is going shifting to other surface as well as going increasing in magnitude also. For that purpose, we require a 3D stress analysis. We say that when rolling and sliding both are present, stresses due to normal and tangential loading need to be accounted. So, load is not only the compressive load and compressive load because of the imparted from the cam surface, but load also will be there because of the friction. So, stress value can be calculated something like that. We assume that cam and follower are x and z plane, there is x axis and a z axis, and perpendicular to that the length of the follower is along the y direction. In that case, stresses can be calculated, stresses due to normal force, stresses due to tangential force, that is a frictional force. Similarly, sigma z stress or normal stress in z direction will be force due to the normal force in z direction and compressive stresses due to the tangential force. Why there is no load as such applied, but because of the connectivity, because of the molecules are interconnected, and there will be a Poisson ratio, finite Poisson ratio is generally 0.2 to 0.3. Some stresses will also induce in y direction, it will not be without stresses. Finally, comes shear stress. We are talking about the shear stress only at the xz. We can because the stresses are all over, but this will be the maximum which we are trying to find out. What will be the maximum value of this? Now, in this case, if I whatever the results which you are going to show, in that case it has been assumed the coefficient of friction is 0.2. We say that whatever the normal force we are applying, it is getting multiplied with a 0.2. Our overall force is 1.2 times of the normal force, but directions are different. This is along the z direction, this will be along the x direction. So, simple 1.2 times calculation may not give all the results. We will be taking a vector assuming the directions, and we will calculate force according to the different axes. If I do the overall analysis, and here the few results are presented, you say that at the cam angle only few degree we have a few results are presented, so that it can be accommodated on slide easily. Contact radius has been repeated, which was shown also in the previous slides. Normal force is fine, the same force which was shown earlier, but you can see the contact stresses. Initially it was roughly 280, now it is coming around 344, is reaching to the 574 maximum. In previous slide we have shown the maximum value as 471 megapascal, while accounting this 473 megapascal. Now, accounting this forces, what we are getting roughly 574, around 101 megapascal is additional, around 20% stresses are increasing because of the force, because of the sliding, because of the coefficient of friction 0.2, which will be accounted. Now, we do not know exactly what will be the coefficient of friction. Will it be 0.1, will it be 0.2, will it be 0.3, will it be 0.4? And when the gross sliding is happening, what kind of lubricant is being utilized here? If we use 2 lubricants, wherever the sliding happens, we use a thick lubricant, or either thick lubricant or use a solid lubricants, then it may give a better results. It will reduce coefficient of friction to roughly 0.2. If we do not use solid lubricant there, and we use only liquid lubricant, the way the whole interface is getting lubricated, then quite possible coefficient of friction will localize increase that from when we are shifting from convex to concave contact, or from concave to the convex contact, coefficient of friction suddenly will increase, because these kind of cam followers are generally supplied with a grease, and which is having a low NLGI grade, which can be easily pumped. If it will be easily pumped by using NLGI grade 1 and 2, then it will not be very effective to keep the lubricant layer at that interface. So, either it should be mixed with some sort of molybdenum disulfide or solid lubricant, and they get the good results. Apart from that, now this slide also shows only the maximum normal stress. It does not show the tangential stress, it does not show the shear stress. And in from previous slide we mentioned clearly that we should give more emphasis on the shear stress. We should not give more emphasis on normal stress. The question comes, do we have experimental data available with us? If experimental data are available with the shear stresses, then we can compare. We can find out the shear stress, yes, and then we compare it with the material strength. Fundamental rule says that if yield strength is some 500 megapascal, shear strength will be around 250 megapascal, or 50% of that. But it appears from this kind of surface fatigue phenomena that stress is not very useful. Many times it gives wrong results. So, people have done extensive studies only on normalized normal forces, introducing along with the some sort of sliding, which gives a better results. And this phenomena is common in a cam follower mechanism, in rolling bearings and gears. So, that is why the results are available with us, just only the normal force and normal force with the sliding, or we say that normal force with the pure rolling and normal force with the sliding. We can utilize those data using the curve fit equation to get some results. Again, it may not give 100% results, but it gives the comparative results to us. So, what I was talking, some material data are available. These are the cam materials. Mostly they use a grey cast iron, or they use a nodular cast iron with the different hardness domains. It is showing this table has 4 columns. K is a constant, SC is surface compressive strength, particularly is number of cycles as also mentioned, that is the 10⁸ cycles. So, this strength for the 10⁸ cycle is more like a endurance strength of metals, particularly in rolling in a fatigue phenomena. In this case the same thing, but endurance, instead of talking about endurance, we should talk about only the surface compressive strength, because it will continuously vary, it will continuously decrease with the number of cycles. If I increase the number of cycle 10⁹, I am sure that this 49,000 will reduce to roughly around 40,000 or lesser than that. Similarly, there are two other constant, lambda and zeta. How these three parameters are connected is something like a zeta minus 10, the log 10 n is the number of cycles, particularly can be given in the 10⁸ cycle, 10⁶ cycle, and there is a lambda. So, there is a relation, a curve fit relation given to us. In other words, if we want to increase the life, we will be able to find out what is the value of k, which is required. If I say I want a cam life to be 10⁸ cycles, now after that we need to choose proper k, proper zeta, proper lambda. So, iterative scheme can be used to find out which result, which material will give me appropriate results. Another is of course, this table shows when we are introducing 9% sliding with a rolling. We say the 9% energy is getting wasted in sliding, it is not imparting relative, it is not imparting the rolling motion. We can see clearly here that whenever there is a 9% sliding, strength is reduced from 49,000, it has reduced to 47,000. From 1,02,000, it is reduced sorry, from 1,02,000, it has reduced to 94,000, right. Similarly, this is reduced with the addition of sliding. Whenever there is a sliding, strength or surface strength is reduced. There is a correlation also available within strength and k parameter. We say if shear strength 10⁸ cycle has been introduced over here, we will be getting some value of k. Of course, E prime here it says effective Young's modulus, and we are talking about the two materials. Material 1 has Poisson ratio nu1 and Young's modulus E1. For material 2 is a nu2 and E2. When we use this shear the surface strength for 10⁸ cycles, we will get a k value over here, and same k value will come over here. So, that means this kind of two relation can be utilized to find out what will be the estimated life of cam follower mechanism. Now, if I find out maximum normal principal stress, which we determined in previous slide, something like this, if we are able to find out what is the maximum normal principal stress, that stress can be utilized in this to find out what will be the value of k for a material. If I know the grey cast iron is being utilized for our purpose, for our cam material is grey cast iron, I can find out or I can estimate maximum normal principal stress. From that we can find out value of k. Once the k value is known and for material zeta and lambda are known, I can find out what will be the life and in number of cycles. And if we know the rotational speed of that cam follower mechanism and how many hours it is operating in a day, we can find out what will be life in number of days. Okay. This will be only relative, it will not be absolute. If you want to find out which material is going to give you the better results and how much better, like will be 50% better results or 100% or more than that, then we can choose proper material based on that. Now, utilizing those parameters, we can say when we are thinking a cam follower is running at a 60 rpm and we can find out what will be life for the grey cast iron with a C20, which has a lower hardness. It appears that this kind of a mechanism or this kind of material will show very low life. It shows only the 16.5 days, much lower life. In real sense, if the sliding is reduced by applying proper lubricant, obviously instead of 9% sliding, there is only 1% sliding or 2% sliding, then this life will increase. Now, if I change from this grey cast iron to this grey cast iron, which has solid lubricant phosphate coated, the phosphate itself is acting as a solid lubricant layer. That means sliding, obviously that coefficient of friction will reduce substantially. In that case, we are able to find the very high life. It comes roughly the 3700 days, which is substantially high life, almost 10 years now. So, that is good. However, when we are increasing speed from 60 rpm to 65 rpm, we are able to find that that is because rotation is increasing, that is also increasing the sliding, that is reducing the life from 16.5 days to the 11.8 days. The life substantial life is reduced. We can say that is around 28.5% life is reduced. What we are gaining a profit in a productivity is hardly 5%. From 60 to 65 rpm, the 5 rpm is increased. So, we are not getting even 5% profit, but loss in the life is almost 28.5%, this is substantially high. That means, we will never recommend the increasing cam follower speed from 60 rpm to 65 rpm. Maybe giving slight advantage on the productivity point of view, but life is compromised severely or loss is much on higher side. Coming to the second material, we can say that it has a more effect. If the speed is increasing from this 3700 days to speed is increased from 60 to 65 rpm, number of days useful life is reduced. Roughly is coming 2300, or much lesser than 50%, and overall reduction in life is coming around 36.3%. Similarly, we use higher carbon higher percentage in this case. When you use higher hardness also, of course, we are removing the phosphate coating, self lubricated coating, we can say that life is reduced in this case. Similarly, for all other material, but one interesting thing is the nodular cast iron, which has a retainability or a much better sliding performance, is showing very high life. Of course, again this will be hypothetical. I can say that that is not going to give a good solution. Quite possible it can avoid the pitting failure, but some other mechanism will come and fail this component. Maybe pitting failure can be avoided, but mild wear removal of the layer cannot be. It is a dynamic process. If the micron level particles have been removed from the surface, clearance will continuously increase. If the clearance is continuously increasing, impact loading will continuously increase, and that may cause a more problem. So, this will be totally hypothetical, and I am saying that in this case we are just considering only pitting failure. We are not assuming any other kind of failure. We are not talking about the abrasive failure, we are not talking about adhesive failure, or we are not talking about change in dimension. If there is a change in dimension, increase in clearance, this life also will be reduced. It is wear cannot be that high, cannot provide that high life. So, in totally what we say that this kind of a mechanism, when we do a wear analysis, we can compare the materials, we can find out what kind of load condition is going to give us good solution. Do we need to reduce the load magnitude? Do we change variation in the load? If yes, whether that is going to be advantageous to us or not. If we find no, even whatever I do cannot change the dynamic load because of the rolling contact, which has inherent load, dynamic load generation, then there is no point to change the design at that point. However, but we can say we can provide a better lubricant, we can reduce the coefficient of friction. I have seen industry are applying now with a two lubricant. They use high energy grade grease. After every 10 hours they re-lubricate the surface where the maximum pitting is occurring, and they use additional grease just for the circulation purpose, so that can take away the particles and lubricate those surfaces which where the severe condition is not been imposed. So, those things are there. We will end with this slide on the cam wear analysis, and in addition to that we are finishing the module 3, which is wear module. We will be starting next lecture onward the fourth module, that is a lubrication mechanisms and lubricant, what kind of lubricants are useful for us or for the machines which we are planning to design or we are trying to maintain that mechanism. And with this I thank you for your attention.